Hi everyone, we will solve worksheet 10. It's about graphs again. So let's start. First, we will decide if the given paths are simple or not, if there's a circuit, and the length of the given paths. So let's start here. So here we have the graph, okay, as you see. So the first one is here we have A, then E, then B, C, then B again. So as you see, we use the same edge 2 times, so it's not simple. And there is no circuit because the starting and ending points, the vertices are not the same. And it's of length here 4. We only count the vertices, the number of the vertices, which is 5. And we subtract 1 here, so we have 4. Okay. And for the second one, here we have A, E, A, D, B, C, A. So the first and the last vertices are the same, so it's a circuit. Okay, and it's not simple because again we have these two vertices which are the same, so we use twice, so it's not simple. And it's of length 6 because we have 7 vertices there and we subtract 1 and get 6. So the remaining paths are homework for you. Okay, and we'll decide for the second question if the graphs are connected or not. This part is again homework for you. So let's start with the first one. It's obviously not connected because these two vertices are not connected, right? There is no path between them. Or you may see that first this and for example this or this and this are not connected, right? So it's not connected. There is no edge between them or a path between them. So what about this B? So it's not connected. Okay. What about B? It is connected because if you pick any two vertices, for example, this and this, you can find a path between them. For example, this is a path which connects these two vertices that I chose. And for example, if you pick this and for example this, so what's the path between them? Let's erase first this one. Okay, so it is this. Okay, there is again a bit path between them, so they are connected. So hence the graph is connected. Okay, you can find a path between any two vertices. As I said before, this is homework. Okay, so let's solve the third question. This is quite important. So we will use the paths to decide if the given two graphs are isomorphic or not. So for the first one, always you should check the 3 invariants, which are the number of the edges, degree sequence, number of the vertices are the same or not. So as you see, they are the same. So we have to decide the isomorphism, the relation of isomorphism, using the paths. Okay, the only way now. So what do? We will count the circuits first, okay? For example, for the first graph, here we see that we have one circuit here, right? And another one on the below of the cube here. And here we have another, okay? So as you see, if you count them, there are 6 circuits here. What about this? Here we have one of them, and the remaining one again similar to this. So we have many circuits, such circuits, and another one is this circle, and last one is here. Okay, so again here for this we have 6 circuits. So we may use these circuits to find an isomorphism between them. Okay, it seems they are isomorphic, right? They all invariants are the same. So let's use these circuits to find an isomorphism. So for example, one of the circuits on this group is U1, for example, U1, U2, U7, U6, right? So we write all circuits here, okay, for G, we have these ones, and for H, we have these ones, okay? So, for example, V1, V6, V5, V4 is a circuit on this, okay? We write each of them, okay, here. So, now let's examine a little bit. For example, for this circuit, we have these vertices, and you see here, we have the same, right? We can match them. So it means the image of U1 can be V1, okay, under the isomorphism that under the function. We don't know if it's an isomorphism yet, but under the function, the image of U1 can be V1, okay, and for U2 we have a candidate, which is V2, and for the rest, here we have these vertices. So, and the other one we can check is this. So we have these vertices. Now on the right for H, we have these ones. So the only vertex whose image is a little bit different is this U8 and V4, right? So the rest again the same. So here we have before the image of U1, U2, and U6. Sorry, the U2, okay, and U7. We know U2 should be V1. The corresponding vertex should be V2, okay, and we have the same. So what about U7? Because we have here U7, it's V7. So we have the same again. And U3, as we guess, it's V3, but we need to change the image of U8. It's not as we guessed before. It should be V4, okay? And for the last one, we can check that, or let's check this one. And yes, this one. So we have U1, U2, U3, U4, okay? So here we have, sorry, I couldn't change the color. So here we have, and we have this one. So U4 should be V8, the image of U4 should be V8, and U8, it's V4, okay, the image. So here we have the image of the vertices. Okay, the only difference, okay, it's for U4 and U8, okay, which are these ones. So we will check now if this function that we construct before is an isomorphism or not. So how do we decide it? You remember that we need to check the vertices, the matrices, sorry. So we write the matrices using this function that we construct. So for G, we have these vertices, right? So we write them here on the top of the matrix and on the left of the matrix. So how do we fill this matrix? How do we know these entries? We use the graph, remember that. So we know U1 is connected with U2, U6, and U8. So there is an edge between all 3 vertices and U1. So we should For U2, we should write 1. For U6, we should write 1. For U8, we should write 1. And the remainder should be 0 because there is no edge between them and U1. So we fill the rest again using this idea. And we have this matrix. What about the second one? Again, we use this function f. So we have these images for these vertices. The order of the vertices for H should be this, should be like this, because we should use f. Okay. For example, we write v1, v2, v3, but not v4, but v8, because the image of u4 is v8. Okay. So we write them as you see and fill the matrix again using this graph. Okay, we know, for example, v1, there's an edge between v1 and v6, v1 and v2, v1 and v4. So here we have, okay, v1 and v2, 6 and 4 here. Okay, so we have this matrix. Now we need to check if they are equal. They are equal because each entry exactly the same, right? On both matrices. So it says that the function that we wrote before, okay, here we found, is an isomorphism. Okay. So for the second part, again, as I said before, you need to check first the 3 invariants, and you see they are equal, and another one using the paths to decide if they are isomorphic or not. So as in this explanation, here we see that G has 2 circuits, okay, of length 5. So for example, this is a circuit of length 5, and this one, this part on the left of this circuit, is another circuit of length 5. So there are too many such circuits. What about this one? There is no such circuit. There is no circuit of length 5 because, for example, here we have 4, a circuit of length 4, and this is also of length 4. Each of them is of length 4, so there is no such circuit. So we cannot find any isomorphism between them, because if we have an isomorphism, and if this is a sequence, for example, this is a circuit, for example, in a graph, then the image of them should be a circuit in the corresponding graph. So we cannot find any circuit of length 5 here, so there is no isomorphism between them. Okay. So okay, for this one, we will determine whether. Okay, there is a problem. Okay, so we will determine if the given graph has an Euler circuit, okay, or not. If there is, we will find such circuit. Okay, we will also check if there is an Euler path or not. Okay, so here we have 2 recalls. I'm sorry. Okay. So first one says that a connected multigraph with at least 2 vertices has an Euler circuit if and only if each of its vertices has a degree. So we can check if the given graph has, if the vertices of the given graph have even degree or not, okay, to determine if there is a Euler circuit or not, okay. And another theorem says that a connected multigraph has an Euler path but not another circuit if and only if it has exactly two vertices of odd degree. So we can also use this theorem. So let's check for B. Okay, so the degree of A is 3, right? We have 3 edges here, right? As you see. And it's not even, it's odd. It's odd degree. And from using this first theorem, we can conclude that there is no Euler circuit, right? Because each vertex should have even degree. But we found one of them, one vertex which has odd degree. So there is no Euler circuit, okay? So there is nothing to find. Okay, so for Euler circuit, I mean. Okay, and we can check the rest, right? If there is a vertex of odd degree, we see D has odd degree too, right? And the remaining vertices have even degree. So using the second theorem, because we found only 2 vertices of odd degree, we can use this theorem. It says this happens if and only if this happens. So we knew before that there is no Euler circuit, but Euler path now, right? So what's that Euler path? So we write it. Here we have the Euler path. Okay, A, C, right? From A to C, and then E, then C again. Okay, you should check by yourself actually to find such paths. And then D, then E, then A, then B, E, B again, and finally D. So we pass through all edges and only once, right? So there is an Euler path, and it is this. Okay. Okay. The remaining are homeworks again. Now the other question is this 5th one. So here we are given this rod, we can say rod. We have bridges on it, right? So we will decide if someone can cross all the bridges only one time, okay, only once, okay, and we want it. We want him or she, her, to back to the starting point, okay, passing through once of all bridges. So we can use this. We can find that by using the graph, the information about the graphs. So we can, for example, write this road as a graph, as in here. For example, so here we have, so they are connected at one point, right? Okay, so, and also these are connected at one point, okay, and this are connected, and so we may see this as one point, okay, below, and here we have another point, and between them we have 3 edges, right? 1, 2, 3, but this is connected to another point. These are connected, so we have another point here, and we have this, okay, and this is, then you write it here, right? This is here, and above we have another edge, this, and this is also connected to this one, right? These ones. So we have 4 here. Okay, so let me write them again. So this and this are on here, and this one, okay, and this one. Maybe I need it. Anyways. So so this is 1, 2, 3, 4, and 1, 2, 3, and 4. Okay. So another one is here, this green one. Okay, and the last one is here. Okay, as in here you see. So we can use this graph to find the solution. So it's as we want the person start the point at some point, at some vertex, and back to there again, right? We need to find the answer of this question: is there an Euler circuit or not? So how do we do? We use again the theorem. So recall that. So each vertex should have even degree. Okay, only this case gives us there's another circuit. So we need to check that. So we see A has 4 edges, right? Its degree is 4 then. And the degree of D is 2, degree of C is 2, and degree of B is 4. So each of them has even degree. It's already connected, so we know that. If it's not connected, then we cannot apply the theorem, okay? It's connected. I should have said that before. And we see any of the vertices have even degree. So we can write an Euler circuit. We know there's an Euler circuit on it. So it means that somebody can cross all the bridges once, exactly once, and go back, return to the starting point. Okay. Now again, the similar question. We need to check if there's another circuit or not. Okay. Okay. So each vertex, here we have A, B, C, D, we see, right? So each of them have even degree, okay? So there is no vertex that has odd degree. Again, by using the theorem, it's already connected. So using the theorem, we conclude that there's another circuit, okay? Thus, it means we can draw such a picture. Okay, here there's a definition of a complete graph of n vertices. Okay, it should be simple and it should contain exactly one edge between each pair of vertices. So here we have for Kn, where n equals to 1, looks like this. And K2 is this, K3, till K6. Okay, so we will decide if there is an Euler circuit or not on these graphs. So we will find only for K4 and K5. So K4 has a vertex of degree 3, right? K4 is here. There is a vertex, for example, if you look at this, it has degree 3. So there is an odd degree, okay? So it means there is no other circuit on this graph. What about K5? Here we have K5. So each each vertex of K5 has even degree. For example, this one, it's 4, 4, 4, and 4, right? So there is no vertex of odd degree. It means there is an other circuit on this K5. Okay. So the remaining are homework again. So we will find the length of a shortest path between A and Z. Okay. Now we will, as you can guess, we will use the algorithm. So first, the starting point is A, so you put 0 here, and the remaining should be infinity. So you look at that, which vertices are connected with A. They are B and C, so we write B and C, and the weights of the edges. So for A and B we have 2, and for A and C we have 3. Okay, here we have 2 and 3. We see the least one is 2, so we go from there. Okay, so for B we have these two connected vertices. They are D and E. Okay, and we know this weight is 5, 2, and we have 5 there between C and E. So here you see we have these 7 and 4. Let's look at again. So we had before 2, and by B we go from B we go D to D. So we have 2 plus 5. We have 7 there. Okay. And what about E? We have, this is 8, right? From A to E by passing through C, we have 8. But from B, we have 2 plus 2, which is 4. So it is less than 8. So we write, instead of 8, we write 4. Okay. And again, there is no connection between Z and any of these vertices. We write again infinity. And now you see the least one is 4. Okay, let's look at that. So from E, there's 2 points, the 2 connected points. We have D and Z. So we had before 4 for E, right? We had before 4, and now we have 1 if we go D. So we have 5 then. 5 is less than 7, so we write 5. We don't change anything for E because we had before the 4, which is the least one. Okay. So what about Z now? If we go from E to Z, we had before 4, and we add 4 again, we have 8. Okay. Here, 8. Okay. We already changed the corresponding number of D because we had before 7 and now 5, and 5 is less than 7. So here we have the last computation is this. Now let's check again. We have 5. We recall that we had 5 here at D, right? We have 2, 4, 5. And now from D, if we go Z, because they are connected, we have them 7, which is less than 8. So we write 7 there. Okay. So 7 is less than 8, and this is the final number, right? Then from A to Z, we can go using these vertices, and the length or the weight is 8. Okay. So this was the last question. If you have any questions, you can attend the office hour, which is on Friday. So see you there.